Hello everyone, welcome to our last part of chapter 3 here. So if you haven't noticed, we've spent a lot of time talking about matter, but the chapter is called Matter and Energy. So this last part 3 here, is going to be a bit of our discussion about energy. We're going to talk a little bit about different forms of energy, what energy is, how we can convert between different temperature scales, and how we can relate kinetic energy and temperature change to each other. So that being said, let's get into it. Like I said, we're going to talk in these set of slides about energy. So energy is sort of the counterpart to matter when we're thinking about chemistry. So matter is kind of the stuff, and energy is what makes it go. Energy is the capacity for something to do work. So energy is what can make something happen. So when we talk about energy, oftentimes we'll talk a lot about forces as well. If you've had a physics class, you probably know lots about force. But it's a push or a pull on an object as a result of it interacting with its surroundings somehow. So somehow we're doing something to change the location or identity or something like that of matter. There are lots of different kinds of forces. You could have gravity, magnetism, friction, electrostatic forces, things like that. But truly, in the end, force can be boiled down to 4 different forces. So the gravitational force, so you think about we're on Earth, we're being held to the Earth by gravity. Gravity is the force, it's that energy change that's holding us here. You might have electromagnetic energy, so that could be like the energy and the radiation coming from the sun, for example. And we have the strong nuclear and the weak nuclear force as well. We won't really talk about those so much, and they're kind of hard to explain, but again, I just want to give you an idea about what forces are. So those are also going to be the kinds of forces that like hold literal atoms together in the end. Through the semester, the main kind of force like we're going to focus on is the force that is the attraction between a positive and a negative charge. So if you think about it, if you've ever played with magnets before with like a north and south pole or a positive and a negative pole, when you put the positive and the negative together, they attract to each other, and you can even get the magnets to kind of like scoot across the desk or something because they want to be attracted to each other. So it's a force that's pulling the magnets together to hold them together, to keep them together. Or 2, there's like a repelling force there too, right? If I put 2 of the same poles of a magnet together, 2 of the same ends, like 2 negative ends together, those are going to repel. They're going to push, so they're not going to go together. Maybe you can try to get them to touch each other, but they're sure as heck not attracted. And you can see that it's hard to move those magnets together because they're repelling each other. They have a force that's pushing them apart in the end. So those are the kinds of things we're going to talk about throughout the semester. So really we're focusing in on the fact that we're thinking about a force as the attraction between a positive and negative charge, or 2 positive charges or 2 negative charges repelling each other. So realistically, in the end, if we're thinking about energy, there are 2 main types of energy that we deal with. All other kinds of energy can be distilled down into just these 2 types. So they're kinetic energy and potential energy. So you may have kind of heard some of this stuff before. If you're into like exercise science, you may hear about kinetics, like kinetics of the body. So that's movement is what we tend to think of with kinetics. So kinetic energy is the energy associated with motion. So it's kind of what we traditionally think of energy. You're bouncing around, you're moving around, lots of energy, woo, 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 kind of a deal. So like airplanes, for example, have a ton of kinetic energy because they have a lot of mass and they're moving very, very fast. So that's a lot of energy that has to keep all of that mass moving. And so we can think about that when we're thinking about airplanes. Again, the kinetic energy is the energy of motion. If you want to take kind of one of the classic physics examples, it's like the motion of going really, really fast down the hill on a roller coaster. So potential energy is the counterpart to kinetic energy. So it's the energy associated with position or composition. So what something is or where it's located. So it's the potential that it could do something. It's sitting there. It could be moving. It's just not moving yet. So it has the potential to move, and we call that the potential energy. And however, how much stored up potential energy something has, that is going to have more potential to have more kinetic energy in the future. So, so for example, here we have water being held back by a dam in this picture. So what's happening is there's a high potential energy up here. Potential energy kind of occurs when you're trying to force something to do what it doesn't want to do. So the water wants gravity to pull it all the way down as low as possible. So when gravity's pulling something, it wants it to be as close as possible as it can to something. So this water up here doesn't want to be this high up. It's the dam that's in place that's stopping it from going down and actually releasing all of that potential energy, okay? So it's potential because it's stored up. If that dam breaks, there's a possibility that that water's going to move. Well, not a possibility. There's an actuality that that water's going to move. But the thing is there's not a lot of kinetic energy there because the water's just sitting there. But the second the dam breaks, that potential energy is converted into potential energy, and it goes whoosh. So this is kind of an energy associated with position, but we might also talk about potential energy in composition. So in chemical bonds, if we can unlock the potential energy stored in chemical bonds, and we can, like, let's say, break apart a molecule, we'll be releasing energy when we do that. So if we have energy stored in chemical bonds, that's a potential energy associated with composition. So it's really fighting to hold those atoms together, but when we break it apart, we can release that potential energy in that chemical bond. So there's kind of energy stored in chemical bonds. So we've talked a bit about potential energy and kinetic energy, but we might also want to talk about the total energy of the system. So in any system, the total amount of energy in the system is the sum of the potential and kinetic energy. So if I'm looking at a closed system, you're only going to be able to ever transfer your kinetic energy and your potential energy kind of back and forth. But as long as you have a closed system, the total amount of energy stays the same. So it's just going back and forth, converting between potential and kinetic and potential, back and forth, as long as you're not intentionally adding more energy into the system. So again, if it's a closed system, we're not letting any more energy in. The amount of kinetic energy plus the amount of potential energy is going to be the total energy. So as we talked about the law of conservation of mass, we also have the law of conservation of energy. I'll give you 3 guesses what it says. So if we have the total energy in a system, it's always going to be constant. That energy is transformed between kinetic and potential energy. So if you gain potential energy, you lose kinetic energy. If you gain kinetic energy, you lose potential energy. They're just going back and forth between one and the other. And oftentimes, too, if we're thinking about a total system of energy, systems with high potential energy want to convert that to kinetic energy to move to a state where they have lower potential energy. So if something is high potential energy, it wants to convert all of that energy to kinetic energy to move to a lower state of potential energy. So it doesn't want to have to be fighting that dam like when we were looking at the picture before. That water doesn't want to be fighting and having that dam holding it in place. It wants to be down into that lower potential energy state where it's closer to the earth and that gravitational force can do what it's meant to do, where it's not being blocked by that dam. So again, systems would rather expend that potential energy as kinetic energy than hold on to it. And so a lot of times, too, wanting that lower potential energy state is going to be what drives a chemical reaction. To break a chemical bond, in the end, you have to put a tiny bit of energy in, but once you put a tiny bit of energy in, you can then break that chemical bond and expend all of that potential energy that's held within that bond as kinetic energy, which will lower the potential energy of the total system. In the end, it'll have more kinetic, less potential. As I mentioned before, all energies can be kind of distilled down to whether they're a potential energy or a kinetic energy. But let's talk about a few more specific types of energy as well, because there'll be some of them that come up throughout the semester as well. So we might broadly have these two big categories, but we can put more specific names on some of those kinds of energy. So we might have electrical energy, and that would be an energy associated with the flow of electrical charge. That would be like when you plug something into the wall, that's obviously electrical energy. When you're using a battery, that's electrical energy. Anytime you're kind of getting that power from an electrical charge. It's potential energy when you're charging the battery. You're adding all of that electrical energy in to be stored as potential energy in the battery that you're going to use later on. Let's say, I'm charging my phone right now. Later on, when I start to use it, I'm releasing that as kinetic energy. Therefore, it's the energy of the motion of making all of the stuff in my phone work so that I can have my phone. Kinetic energy, as an example of like the flow of electrical charge, would be like the electric current that's running my lights above my head, for example. So you're getting that electrical current expended by actually powering the lights. So it's kinetic energy when the lights are being powered. We might also talk about thermal energy. So this is going to kind of feel weird because thermal, we think of temperature, but thermal energy is actually the energy associated with the random motion of particles, which has something to do with temperature. We'll talk about that in a second. But again, it's the energy associated with the random motion of particles. So we'll talk more about thermal energy. We'll talk about heat in a minute. But again, it's a form of kinetic energy because it's associated with the motion of particles, how those particles move, how fast they're moving, kind of a deal. Chemical energy is the energy associated with the position of the atoms in a molecule. So chemical energy is going to be like the energy that's stored in those chemical bonds. And different types of chemical bonds hold different amounts of energy. So some of them are very, very energetic. Some of them aren't. It's a form of potential energy because it's based upon how the molecule is arranged. So that's that position and composition fact, which makes it potential energy. Potential energy is also stored in the interactions between particles, like the interactions, for example, that hold liquids together and solids together. That's a form of potential energy when they're being held together because they'd rather be broken apart, flying around, not interacting like a gas. But there's something happening in the system where they're storing potential energy in those interactions rather than expending it as kinetic energy. So let's talk a little bit about how energy relates to physical and chemical changes. So physical and chemical changes are associated with a change in energy as well. We talked about maybe a change in the state of matter or in the way something looks, but it can also be, it is also associated with a change in energy. So water evaporates from your skin. Let's say you're sweating or you get out of the pool or you go to the sauna or something and you're walking out. You're going to start to have all of that water evaporate from your skin. That's a physical change. It's water when it's on your skin. It's water when it's a gas when it's no longer on your skin. So the water molecules take some of the thermal energy in your body, and it gives that energy to the water molecules on your skin so that it can go through this physical change. So there was an exchange of energy there. The water took some of the thermal energy from my arm to complete this phase change, and my skin gave up that energy to make me feel cooler. Like when you sweat, that's why you feel cooler, because you're giving off that energy so that you can make the sweat on your skin into a gas. So when it's evaporating, it's taking that heat away from your skin because it's using it to go from a liquid to a gas. And as I mentioned before in the last set of slides on part 2, when you light a lighter, it's also a chemical change. So by burning the gas, by transforming the molecules from butane to oxygen, or butane and oxygen to carbon dioxide and water, energy is released into the environment. You know, that fire is hot. You can feel that heat energy coming out into the environment. So that chemical change is associated with a change in energy as well. Let's talk a little bit about how energy relates to chemical molecules and reactions. So remember, systems that are high in potential energy want to convert that potential energy into the lower potential energy in the system. So it wants to have less potential energy. So it's like, I'm going to expend this as kinetic energy so I can settle down and be lower in potential energy. Of course, again, if it's a closed system, the total amount of energy stays the same. So this kind of fact of wanting to lower the potential energy of a system drives a lot of chemical reactions. If a bunch of molecules can use just a little bit of starting energy to rearrange their particles into that lower potential energy state, they absolutely will do it. So some chemicals do have a lot of potential energy stored in their chemical bonds. This is, of course, chemical energy as well. And this might be like TNT, for example. So it's explosive because it only takes the tiniest little spark of energy to set off a chain reaction of those molecules moving from a high potential energy state to a low potential energy state. And there's a ton of energy stored in those bonds in TNT because of how the chemical bonds are arranged. So there's a lot of energy stored that is released when we change that state of that system. So while TNT does have a lot of energy stored in it, remember all chemical bonds have a different level of energy within them, potential energy within them. So some chemicals don't actually have very much potential energy stored in their bonds, so they're much more stable then. They're already very close to the lowest potential energy state or in the lowest potential energy state they can be in, so they want to hang out and they don't really want to change. It takes putting a lot of energy into those systems to get them to change because they don't want to, because they're already close to that lowest potential energy state. So again, we're talking about potential energy and kinetic energy. It might not feel like a very chemistry topic, but what's important here is that you know that the change in potential energy and the change in kinetic energy in a system are what can drive chemical reactions, and all chemical bonds have different levels of potential energy stored in them. So some are very reactive, want to change, want to let go of that potential energy. But if they don't have very much potential energy, they're expending all of their energy as kinetic energy, they tend to be a little bit more stable, and it takes a lot of energy, therefore, to change them. Okay, so let's talk a little bit about how energy and temperature relate together as well. So we kind of talked about how it affects chemicals and chemical reactions, but also one really, really important thing is how energy and temperature relate to each other. So temperature is the measure of thermal energy in a substance. Remember, like you might think you're measuring like how warm it is outside something. That's kind of what you're thinking in your head. But really what you're doing is measuring how fast those gas particles in the air are moving around when we measure the temperature. We're measuring that random motion of the particles. So again, thermal energy causes random motion of particles. So this is called Brownian motion. I think it's kind of a cool name. So particles are always constantly wiggling around doing something as long as they're over the temperature what we call 0 Kelvin. So if you see that K, it's just like how we have degrees Celsius, it's just like we have degrees Fahrenheit. You can have a Kelvin as a temperature scale as well. So as long as we're above 0 Kelvin, particles are constantly wiggling around. Everything is constantly in motion, jiggling, moving, having a good time. So we call 0 Kelvin absolute zero. So at this point in time, if you hit absolute zero, particles no longer move and everything stops. We haven't actually, I don't believe, ever been able to achieve 0 Kelvin in the lab setting, but that's hypothetically what would be happening in that scenario. So what is a Kelvin? Kelvin is 273.15 plus degrees Celsius. And it's this number because absolute zero occurs at negative 273.15 degrees Celsius. So Celsius and Kelvin are very directly comparable. Again, you just add 273.15 to the degrees Celsius to get the Kelvin value. So Kelvin occurs, or 0 Kelvin occurs at absolute zero, where that Brownian motion stops, where there is no more thermal energy in a system, at negative 273.15 degrees Celsius, also called 0 Kelvin, also called absolute zero. So it's kind of an interesting thought, and there are lots of things we think might happen in physics when we reach that point, if we can get something to reach that point. But again, I don't believe we've gotten that far yet. If we want to talk about heat, when we're saying, oh, it's so hot outside, what we're talking about is the transfer of that thermal energy. So some particles giving up their thermal energy to other particles. So heat is that measure of thermal energy. So if you're saying it's hot outside, there's so much heat, it's because your body's taking on some of that thermal energy from the environment. So temperature is what we use to measure thermal energy, and heat is how we talk about thermal energy moving from one thing to another thing. And so one really important point I want to make here that is very specific, that's really kind of cool in my mind, is that temperature and kinetic energy are directly related to each other. So as temperature goes up, kinetic energy goes up. As kinetic energy goes up, temperature goes up. So if you change one, you change the other. It doesn't matter which you change, the other is going with it too. So when temperature goes up, particles wiggle faster and faster and faster and faster and faster. And this is why we can change things from solids to liquids, liquids to gases, okay? So if I'm raising the temperature from a solid to a liquid, what I'm doing is I'm putting more thermal energy in, so my particles are going from wiggling like this to I'm moving more to I'm now slipping and sliding past my neighbors, okay? So it's not quite so rigid. Because I have enough thermal energy, I can just kind of wander around and do a bunch of stuff, whereas solids tend to have a lot less thermal energy because they're just boop, 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 versus that big slip and slide motion. And when I have a liquid that's slipping and sliding past each other, I continue to raise the temperature, I'm continuing to raise the kinetic energy, and now I've got gas particles flying around because I've broken apart everything. It's no longer interacting. The particles are wiggling faster and faster and faster, on and on and on. So temperature and kinetic energy are directly related. It's how we can talk about phase changes, and we'll talk a lot more about how temperature and the particle, or the motion of particles, are related to each other when we talk about gases too. So when that temperature goes up, the particles wiggle faster and faster and faster. You're increasing the kinetic energy, and that's what allows us to change states of matter, for example. So it's really important that you do know that temperature and kinetic energy are related to each other. So I mentioned it just a little bit while we were on the last slide talking about how energy and temperature are related. I mentioned that we had kind of different scales there. We have degrees Fahrenheit, we have degrees Celsius, and we also have the Kelvin scale as well. So I want to talk a little bit about these scales and how we can compare them, because we may need to go between all of these different scales, okay? So the one we're definitely most familiar with here in the United States is the Fahrenheit scale. So that's kind of based more on how humans experience temperature and things like that. So if you check out our scale over here, you can see that water boils at the top. Water boils at 212 degrees Fahrenheit. And water freezes at 32 degrees Fahrenheit, and there's 180 degrees between there. It's, again, meant to be a more human kind of based experience scale. If we have Fahrenheit here, we may want to convert to Celsius. So if we have a value if we have a value in Celsius, we want to convert to Fahrenheit. What we do is we take 1.8 times that degrees Celsius value, and we'd add 32. And if we want to get to Kelvin, we should always convert to Celsius first. So we could use, I'll just show you this. So if we're going from Fahrenheit to Celsius, we have degrees Celsius is Fahrenheit minus 32 degrees divided by 1.8. So that's Fahrenheit to Celsius. And over here, we'll look at those conversions in just a second. But again, Celsius is actually based upon when water boils and freezes. So in Celsius, water freezes at 0 degrees and it boils at 100 degrees Celsius. So there's this 100-degree gap there. So a Fahrenheit degree is much smaller than a Celsius degree. Again, if you have a Fahrenheit value and you want to go to Celsius, what you'll do is you'll take Fahrenheit minus 32 divided by 1.8. So that's the idea there. And so we can also talk about Celsius and Kelvin. Remember, Kelvin is based upon that absolute zero value. So absolute zero is 0 Kelvin, and that occurs at minus 273.15 degrees Celsius, okay? So 0 Kelvin is the same as this value, So we always just take our Celsius value and we add 273.15 to get Kelvin. If you want, again, go between Fahrenheit and Kelvin, please stop at Celsius in the middle. So you can see here, if we're looking at the scale again, that at 0 Kelvin, we're at absolute zero. We're at minus 273.15 degrees Celsius. At 0 degrees Celsius or 32 degrees Fahrenheit, or where water freezes, that's actually at 273.15 Kelvin. So at 273.15 Kelvin, that's where water freezes. It may seem like a lot, but again, it's based upon that conversion between these two scales. And then it's another 100 steps, 100 kelvins to get up to where water boils at 373.15 Kelvin. So a Celsius degree is the same space, same width as a Kelvin is, but again, they're different in size than that degrees Fahrenheit. And one point here to make quickly, it's not degrees Kelvin, it's just Kelvin. I don't know why we had to do that differently, but we did. So you never use that cute little degrees circle, the little circle here that represents degrees. You would never put that with a K, and you would never say degrees Kelvin. I would just say 273.15 Kelvin, for example. Okay, so I showed you this graphic on accident and then for real just a couple seconds ago. So it does show us how to convert from Fahrenheit to Celsius. Celsius is what we'll be working in most of the time. Anytime you take a temperature in lab, it'll be in Celsius. It's what we use in science. So Celsius is what we usually be using. So if somehow you have a Fahrenheit temperature, you want to convert to Celsius, you may need to do something like that. Or most of the time what we'll be doing is converting from Celsius to Kelvin, so we'll be adding that 273.15. And actually this graphic from the book is kind of weird because it's trying to tell you how to go from Kelvin to Celsius. If you're at Kelvin and you want to go to Celsius, this should really say something closer to K minus 273.15 equals degrees Celsius. It's just the opposite. So if you want to go from Kelvin to Celsius, you're going to subtract. If you want to go from Celsius to Kelvin, you're going to add. So let's go ahead. We're going to do a couple of examples here. So I'm going to help work through these with you so that you can have a chance to see how temperature conversions work. So the first example you see on the screen is 70 degrees Fahrenheit, and we want to convert that to degrees Celsius. So what I would do if I were you, I will always give you these, I will give you the equation to go between Celsius and Fahrenheit as well as to Kelvin. I'll always be giving you the two equations you see on your screen there, here, and here. So you'll be able to look those up. I'll post them as a resource as well. So if I want to go from Fahrenheit to Celsius, what I'm going to do is I'm going to look for some sort of equation that relates those two things, and it happens to be the one on the far left here. So if I want to go from Fahrenheit to Celsius, I'm going to use this equation. Degrees Celsius equals degrees Fahrenheit minus 32, all of that divided by 1.8. Okay, so now that I have that done, what I'm going to do is go ahead and plug my values in. So I know degrees Fahrenheit, and I'm looking for degrees Celsius. So if I have degrees Celsius, that's going to be my 70 for my Fahrenheit minus my 32 divided by that 1.8 value. So I find that I have degrees Celsius equals, let me get my handy dandy calculator. And so I would type into my calculator 70 minus 32. I'm going to go ahead and press enter or equals at that point, and then I'll divide by 1.8. Throughout the semester, one piece of caution I have to make with you is that the one thing I want to say about this is that you have to be certain that you're typing things into your calculator well. So what I'll often do with this too is post the picture of my calculator screen so that you can start to see how I'm typing some things in. There may be different ways to type it in, and I'll try to show you that too. But it's very important that you learn kind of the mathematical aspects of typing things into your calculator. So I got 21 degrees Celsius in this case. So 21 degrees Celsius is about the same as 70 degrees Fahrenheit. So if I wanted to work through example 2 on your screen, example 2 says 345.783 degrees Celsius, and we want to convert that to Kelvin. And again, I'll always give you the equations that you see. So here I have the equation Kelvin equals degrees Celsius plus 273.15. I'm not going to choose this original equation we used in example 1 because it's only relating Celsius and Fahrenheit. Here I'm going to look for an equation that relates Kelvin and Celsius. Here again we're just going to plug our value in. Kelvin equals 345.783 plus 273.15. That's pretty straightforward to type into your calculator. You can just add them up there. So 345.783 plus 273.15 is going to give me 618.933 for, that was a bad 33 for example. That's kind of how that's going to work, and then we'll do one really quick going from Kelvin to Celsius. So in my example 3 here, I want to go from 674 Kelvin to degrees Celsius. So in this case, what I'm going to do is I could just plug into that equation I just used again. Again, I'm relating Celsius and Kelvin. So in this case, I'm going to put the 674K where the K is, and I'm going to have my degrees Celsius plus 273.15. And so if I subtract that 273.15 minus 273.15 from both sides, I end up getting that my degrees Celsius equals 674 minus 273.15. So then I get 401 Kelvin. Sorry, degrees Celsius. I went the wrong way. Degrees Celsius. So that's kind of the general idea there. They're pretty straightforward. Just look for the correct equation that relates them to each other. And then plug and chug is what we call it. Plug in for the correct option and solve the rest of the math. But this is pretty straightforward here. We'll always go from Fahrenheit to Celsius, and then we can go back and forth between Celsius and Kelvin, just doing that addition and subtraction. I have posted the answers to this stuff here. There are more practice examples you can find in your textbook as well. But that was a quick note about converting between temperature scales. But other than that, I do believe that is all of Chapter 3. So we finished everything up. We talked a bit about matter, classifying matter, what it is, different ways we can classify it. We talked about how we can change matter in physical properties and how we can measure those changes in properties. And we've got physical and chemical changes, physical and chemical properties. And then we talked about how energy is related to matter. Why it matters to us is that it is talking about the speed and motion of molecules. It's going to energy is what drives the change in a chemical reaction. And we wanted to talk too about how temperature and energy are related, that the higher the temperature, the higher the kinetic energy, the more molecules are moving around. So that's Chapter 3. Hope